Okay, so in this video, we're going to be talking about microwave kinetic inductance detectors for exoplanets. Now, these are short form for MKIDs, and on the screen right here, we have a little image of what an MKID really looks like. And these really tie optics and RF engineering into one nice technology used for detecting exoplanets. So, how can we detect anything about exoplanets? This is a big question that we can answer in this video. So, here's the overview for what we're going to be talking about today. Now, essentially, this is the engineering problem and the steps that we need to solve them. So first, we need to gather as many photons as possible. And the way that we do this is by having a bigger aperture, right? So the bigger the aperture, the more photons can come into this aperture. Then we want to focus those photons into a point. So that's the geometry of our reflector. So usually these are parabolic dishes because just the geometry of them allow parallel lines to come and focus into a single point. And then we want to place a detector at that focus point, but not exactly at the focus point. We want to shift it a little bit because we're going to have an array, like a camera at that point. And then we want to filter, amplify, and do our signal processing. So let's just go over a bit of the physics. So here we have our Maxwell's equations. Well, these are pretty famous, but we're going to go over the first two just so we could get a little understanding of some fundamental things that we need to know. So first one says storage of electric energy right here. And when we have a capacitor, we know that DC, when you just connect a battery to a capacitor, we know that electrons cannot flow from one side to the other because there's no straight up conductor between them. But we know that they can store energy due to the first Maxwell equation. And just the fact that there is no direct contact, we could see that our resistance is going to be infinity at a low frequency, right? Like no electrons can flow through, but as you start jiggling, as you start adding some frequency, now we could get some impedance. So essentially, impedance is inversely proportional to our frequency. And then we have our inductor, which is mathematically kind of like the opposite boy of the dude. So it's kind of acting as an AC choke. We straight up have a connection from one side to the other. So at low frequency, DC can just travel across because it's just a conductor. But as you start jiggling that frequency, your impedance will increase, and theoretically, it'll hit infinity. If you start jiggling that frequency, no current can really flow through. So the beauty comes from when you connect the inductor to the capacitor, we're going to have resonance. Now, the nice mechanical analogy of this is the mass spring system, where you have two energy sources, potential and kinetic. You have the speed of this mass due to gravity, and then you have the potential energy stored in the spring, and they swish swash back and forth. Same thing goes for the electrical equivalent, where you have magnetic energy stored in the inductor and electric energy stored in the capacitor, and they swish swash back and forth if you have no losses, right? The mechanical equivalent to that would be like air resistance, and the electrical equivalent would be like resistance in the connection points between your inductor and capacitor. And we know from circuit theory that we can create filters out of inductors and capacitors if you connect them in different topologies. So you could get band pass, band stop, low and high pass filters. But now we need to come to a realization. If we take a look at the middle row here in white, well, we say if we have 20 nanohenries, 10 picofarads, we get a resonant frequency of 300 megahertz, and that's 300 megahertz, 300 million meters per second. Let's just say that's C. That'll correspond to 1 meter wavelength. So 1 meter, right? But if we decrease the capacitance and inductance, that's shown in the purple rows, we're going to have wavelengths of 10 centimeters to 1 centimeter. And if we keep decreasing the inductance and capacitance, it's going to get smaller and smaller and smaller. So if we have geometries of metal on that magnitude, on the magnitude of centimeters and millimeters, well, some really, really interesting effects can take place. And that's what we're going to talk about here, RF and microwave engineering. So let's consider a PCB trace, which is on the magnitude of centimeters and millimeters. And if we zoom in, we're going to see that if we take a look at a single microstrip line, right, we have the ground plane, we have the actual strip line, and between the ground plane and the strip line, we're going to have some capacitance, and it's a very small capacitance, right? A very minuscule amount of capacitance. We're going to also have some inductance along that length, a very small amount of inductance, and then there's going to be resistance and conductance. But the key points here is there's a very small capacitance and a very small inductance, and it turns out that they resonate in the RF and microwave frequency ranges. It really depends on the geometry, but they're in the gigahertz range, right? Those are the capacitors and the inductances you get from small PCB traces like this. And another very important thing is changing your line length, right? And when you change your line length, you're really changing your input impedance. So you could create an inductor or capacitor by just changing the length of a line because we're going to have a different phase amount. And really, a capacitor and inductor are really described as a phase change. Um, but yeah, phase change in your currents and voltages. And here is the Smith chart, which is a mathematical tool used to design radio frequency circuits. It really looks really beautiful, I'd say. But what we could come to realize is that we could have shapes of metal, as you see on your screen right now. There's different zigzags, there's different stubs, there's different geometries, and really these are circuit components at microwave and radio frequencies. It's not at low frequency, we can say, oh, we have a capacitor right here, and we're gonna connect the wire to this inductor over here. And the wire doesn't really matter because we're at low frequencies. They're in the magnitude of hundreds of meters or whatever, lots of meters. But when we're in RF, right, 1 GHz, 3 GHz, they're in centimeter lengths. So now there's gonna be a phase change along those centimeter lengths. So now we get an inductor or a capacitor just because we have phase change along a length. Now what we could come to see is something really interesting about superconductors. So imagine if in that LC resonator we had that capacitor and we had that inductor, but imagine the inductor was a superconductor inductor. And a property of superconductors, you could read about this like Cooper pairs and quasi whatever. I didn't really look too much into it, but when a photon hits a superconductor, it changes its inductance. It's called the kinetic inductance. So we have a light variable inductor, which is essentially what superconductors do. So what we can see here we have an inductor and a capacitor, and when a photon of energy HV hits that inductor, it's going to change the inductance. And when inductance changes, we're going to change our resonant frequency. So if we place uh, a capacitor and superconductor in parallel at the focus point of this dish where we're allowing photons to hit, we're going to see changes in our resonant frequency because different photons are hitting them with different energies. And we're going to get shifts in our resonant frequency because that inductor is light dependent. But that's a 1 pixel camera, I would say, right? We only have 1 pixel. But imagine if we had an array, multiple of these inductor capacitors in an array, then we could get an image. So I'm gonna skip this slide actually because it's really unneeded. So if you really zoom in into a MKID, a microwave kinetic inductance detector chip, what you'll see is when you zoom in, you'll see something that we have on the left side. We see a really large kind of yellowy beige object connect to a more gray object. Now, the larger object is the capacitor. So that has some capacitance associated with it. And if you really take a look at it, each of those larger shapes, if you compare them to the other ones, they're all different, right? No two of those capacitors are the same. If you really take a look. And if we take a look at the more gray object, now that's a superconductor inductor, and they're all the same, right? So the larger objects are all a little different, and then the smaller objects, which are the inductors, the superconductors, are all the same. Now, what that leads to is that we have uh, different channels essentially, because each of those capacitors will change the resonant frequency a bit. So that's what we see in these blue graphs right here. Each of those dips correspond to an individual pixel. Now, when a photon hits those pixels, we can have different readouts per channel. So that's where the red line is zooming in onto, and we see a green and a red and a blue dips. That's corresponding to individual photons with different energies hitting those detectors, right? We have different pixels because they're separated by the capacitance. And then we have separated readouts because the inductance is changing from whatever photons hit it. So now we have a camera that's an individual photon camera that's telling us which energy of photon is hitting that point in the detector. And here's a paper that used MKIDs and other optical and other technologies. But if you take a look at this paper, they actually use the MKID to help them take a picture of this companion with HIP 1009. And here are some telescopes that are going to use or already using MKID. Thank you.